Hello. My name is Avril. On behalf of the Cathans River Education Alliance and the Brunswick-Topsham Land Trust, I welcome you here tonight to learn about our climate system and our tipping points. It's a big deal. Here is how a scientist who recognized evidence of global warming in 1975, here is how he described what he was seeing. We are poking an angry beast with sticks. And now, 50 years later, we're still at it. We rely on fossil fuels for most of our energy. The CO2, carbon dioxide in our atmosphere is steadily rising as our temperatures and extreme weather events in the whole world. It's time to wonder now, I think, about understanding the tipping points that we face. The Cathans River Education Alliance and Brunswick-Topsham Land Trust are partners in conservation and education. Addressing the impacts of climate change is part of our mission. And land conservation, as it turns out, is one of course, many remedies to help with maybe reducing climate change. I don't think we can count on preventing it. Maine has a climate action plan, which probably most of us know about. And it calls for our conserving 30% of land in the state of Maine. We want to play our part in assisting Maine to reach that target. Our land trust aspires to conserve 30% of the land right here where we live in our towns of Topsham, Bowdoin, and Brunswick. We have a good track record. We have conserved 3,300 acres to date. We plan to do more so that we can reach that 30% goal locally with the help of our members and our communities. Truthfully, I think we learn about tipping points for the benefit of our children and our grandchildren. This is a long-term situation. Okay, now I'm really happy to introduce Dr. John Lichter, our speaker. He's a teacher of biology and environmental science at Bowdoin College. And he's here to explain the basic science underlying our climate system, the history of our climate system, and potential tipping points. When John was at Bowdoin, he was the director of environmental studies, and he did a lot of research. And this is where I really need my notes. He researched the effects of carbon dioxide on forested ecosystems, and he did research on the ecology and history of Marymeaden Bay and Maine rivers. And that's an oversimplification. Most recently, he studied ecological recovery in coastal Maine. What a background for telling us about our climate and where it and we may be going. John.
So I'm guessing that you can all hear me well enough.
Yes.
Okay, hopefully. So I'm an ecosystem ecologist. I did retire from Bowdoin College several years ago. And a few weeks ago, the Citizens Climate Lobby asked me to come in and talk a little bit about the tipping points at one of their meetings. And while I did that, and with some of the group agreed that just a lecture that talked just the basic science about the climate system would be useful for people. So I went back to my notes from teaching probably 10 years ago and pulled out a bunch of slides. Now this is going to be a little faster than I would have taken basically 2 hour-and-a-half periods to cover some of this in class. But you're not going to be, you don't have to take an hour exam either. And a lot of these things, or a lot of these topics, the circulation, Hadley circulation, it's pretty intuitive. The Coriolis effect really isn't that intuitive, but there's all kinds of animations you can look at online. You really got to think about it a bit to get that. And then ocean circulation and climate variability, I think aren't, you can grasp that once we sort of get to how the system works. And anyway, so we'll move through those relatively quickly and then get to warming and the tipping points. Okay, otherwise we will be here all night. Should I use You're not turning up?
Yes.
Okay. Okay. So these are data from NOAA. These are sea surface temperatures. And we see the red is warm and going yellow to blue. So why is it that this pattern shows up, day after day? Why is it that the equator area is warmer than the rest of the high and low latitudes?
More sun.
Pardon?
The sun.
Okay, the sun, but what about the sun? I mean, why is it sun warm there more than the high? Okay, it's more direct, perpendicular through the atmosphere. What else? Okay, it's a little bit closer, but that sun's a long ways away too, so it's a little bit closer.
It shines there more during the year. I mean, it's shining in there the whole time.
Okay. The biggest thing, so someone mentioned it's more direct. I think it interacted with this one. Yes? Okay, I'll try not to do that again. So it cuts through the atmosphere.
There you go.
Okay, technology is right. Okay, it cuts through the atmosphere.
You have to stay away from the speaker. Step away from the screen. There you go.
Does this work? Okay, it's cutting through the atmosphere more directly. And notice the area. So a certain volume of light coming in covers this much area here. But see how, because of the curvature of the Earth, it just spread out more at the high latitude. That's the biggest thing. So it's just this, the density of photons coming in is lower. It also is bouncing off and reflecting off of clouds and so forth in the, and there's more atmosphere there. So that's the biggest reason. Okay, so the sun's rays penetrate the atmosphere more perpendicularly. Equal volumes of solar radiation are spread over larger areas. Okay, very clear pattern. Okay, this sets up our circulation. Okay, so basically the uneven heating, this is what drives global climate. It can't stay that way. That heat's going to disperse north and south. It's just physics, right? Okay, now let's think about just another idea, convection. You're all aware of a radiator, a hot water radiator like that. How does that work? I mean, it's just pretty simple. Hot water goes into the thing and it warms up.
And the warm air rises.
It warms the air around it and the air disperses. Does it disperse randomly?
It rises.
It goes up. Why does it go up? There's more energy, molecules are bouncing around, it expands, it becomes less dense than the air above it, so it pushes up that way. Okay. Differences in density. Okay, so as that air moves up, you can see it move in the pages. Is it creating a vacuum within the... Why not? I mean, it would, except air comes in to replace the air that went up. Where is it coming from? In at the bottom. Okay, this is convection. The fire does the same thing. If you've been close to a big fire like that, the wind is screaming into it. It's pulling that in there. Okay, convection is a lot of the way air moves in the climate system. And also, maybe in an analogous way, not exactly the same, but the ocean currents. Okay. So, given convection, given the pattern that we have warm around the equator, what would we expect to happen?
Warm air will go north and south.
Okay? It's rising at the equator, it warms at the equator, warm air can hold a lot of moisture. So a good portion of the earth is water. It warms that energy, it's basically warm, wet air rising. It's like a permanent low pressure system. As the sun rises every day at the equator, it's starting to warm things up and clouds, water starts going up. Okay? Okay, so just like the radiator, it's pulling air in from both sides, right? Okay, so there's some wind coming into this convergence zone of air. It rises. Does it keep rising until it goes up in outer space?
No.
At some point it's shunted north and south. Okay, this is basically the Hadleys. Okay, push the wrong button. Okay, here we go again. Air rising, it's warm, wet. As it rises, it cools. The air cools. So you have warm, wet air rising and cooling. What happens then? Afternoon rain. Okay, so at some point it reaches the water condenses. It basically, as it cools, it hits the condensation point and the water drops out there. So you have a lot of warm, wet water rising. It gets at some elevation and it basically has to fall out. It's being pushed from the bottom, and this is why the rainforests are where the rainforests are. It's like a permanent, low pressure zone with a lot of rain coming in. Okay, and that's shown here. Let me see if I can work this differently. It doesn't like the slide mover. Okay, anyway, again, the air has to move north and south. Now, at some point, depending on the strength of the sun, it's pulling air in this way, but there's a finite reach there. At some point, air that's up higher has the added force of gravity working on it, and so it starts pulling air from above too,
that's coming in this way. And this creates a downwelling of air. And so here we have basically cool air that's risen all this way. Now it's dry and it's sinking. As it's sinking, it warms. Why does it warm? Because there's more air above, weight of the air above it. It's just the opposite of at the tropics, where there's less and less air above it, so it cools. Okay, here it's warming, but it's already dry. Warmer air can hold more moisture. It's already dry, and it sucks up whatever, when it hits the earth, it sucks up whatever moisture's there. And so this is where the deserts are. If you look at a globe, it's not that simple, but you can see, it's pretty much like a band at 30 degrees or so north and south. Okay, this air splits both directions. And so again, this subtropical jet occurs where just air masses of different densities are meeting. The polar jet we're more familiar with, and it's more predominant. This air moving up this way hits the very cold Arctic or Antarctic air, which being much colder, it doesn't mix well. And so this air is like it's being pushed up a mountainside or something. It won't, even though it's air, it doesn't mix readily. And that is where the polar jet is at high. Also, this is a lot of our weather systems where there's a cold front coming in. Pushes the warmer, moist air up until it has to rain out. Okay. I got one too many things here. And now they're not working. Okay, that just says what I just stated. Okay, Earth's precipitation. That's the pattern over like 25 years. So you see the rain through the Pacific, in the tropical regions. You see the very dry areas north and south, which expand into the deserts we know. It's Sahara. And look at the rain belt down here then, which would be, where the westerly airs are running into the polar cold air mass there. Same on the north side. Okay. Now, if the planet had no land masses, this would be very uniform and predictable. The land masses are changing things because land warms up quicker and cools down quicker than the water does. And it's also adding water in places like the Amazon with a lot of trees, or adding water to the atmosphere. Okay, Coriolis effect. Okay, if we have a point here at the equator on this planet, it's going to rotate. Another one there. Let's say in 1 day's time, which one has moved further?
The equator.
At the equator, right? It's got further to go in the same amount of time, so its angular velocity is greater. So this is maybe a little simplistic, but I think you'll at least get the idea of the Coriolis effect. I just watched a Ken Burns documentary on the Revolution and Benjamin Franklin and so on. So I was thinking of like these, British man-of-war ships firing cannonballs. And so if we think of that top star as a British man-of-war, and the star at the equator as a French frigate, and let's say they can shoot a cannonball that far and they can see where they're shooting it. And the Earth, and that planet is rotating. Okay, so if the British man-of-war aims right at the French frigate and fires that cannonball, and it takes an hour for the cannonball to get there, does it hit it, the French frigate? Why not? Okay, it's moved. What does that look like from if the French frigate could watch that cannonball coming at it, what would it look like? It looked like a left-handed pitcher throwing a big curveball at it, right? Okay? Okay, that's intuitive, but going the other direction is not so much. If it was the other way around, so the French didn't learn anything from the British shot that missed, and they shot right at the British man of war, what would that look like to the British man of war? It'd be looking the same way. It'd look the same thing. It would miss, but it would miss to the front of it. It'd be out. The cannonball would be out in front, not behind. Okay, and the reason is because that cannonball, when it's fired from the French frigate at the equator, as it's fired, it's actually moving. It has more angular velocity. It has the angular velocity of the equator, but it's moving over parts of the Earth that have less and less and less angular velocity. So it's moving faster this way, and conversely the other way around. Okay, now that's a little simplistic, but I think you get the idea. And it really influences the climate system. Okay, oops. I mean, this is what we just decided. If you're on the red, if you're at the red dot, and the ball basically looks like a curveball that's totally missed. Okay, what about winds then? Okay, so in other words, if we have air moving away from the equator in the northern hemisphere, it's bending to the right, southern hemisphere bending that way, it's actually going faster than the rotation. And if it's going towards the equator, it bends the other way. There's the clockwise and counterclockwise rotation. Northern hemisphere and southern hemisphere, right there. Okay, we have winds like that, okay? Here's, maybe it's that speaker, yeah. I'll just stay away. Okay, anyway, you see the winds going toward the equator. You see the winds going away from the equator. Those are called the trade winds, predictable, east to west. Those are the westerlies that we're all familiar with. And the cold air at the top just doesn't mix well, right? It's not that it's outside of the system. It does come, it does come down and influence our weather from time to time, but same thing here, okay? So that's the Hadley cell, and I mean, some of the elevations are exaggerated just to show the effect, but okay. Okay, hurricanes. Hurricanes are natural heat. So hurricanes are just a way that energy at the equator is being dispersed north and south. A rather fantastic way. They're natural heat engines. Heat engines are anything that's taken, a concentration of heat and moving to a lower concentration and doing some work involved. Okay, so a hurricane is doing a lot of work. Evaporation consumes energy. Okay, so all that water that ends up in the hurricane evaporated off the ocean, that consumed a lot of energy from the tropics. When it condenses, it gives off energy in the atmosphere. So water's heavy. That's a lot of work moving all that water up in the sky and then having it just dissipate up there. Okay, the spin and direction of hurricanes are influenced by the Coriolis effect. This is a picture, I think this was Katrina. It's just phenomenal amounts of energy. I remember being in North Carolina at one time where there was 6 inches of rain running down the street for like a couple of hours, that deep. It was amazing. I think that was Hurricane Frank back in the 90s. Okay, the paths of hurricanes, are influenced by the Coriolis effect. This is showing, okay, so this is the seasonal effect. Okay, we have seasons because, of course, the Earth isn't the rotation axis isn't perpendicular, but it's tilted, and so that's why it causes our seasons. And the in our summer would be the convergence zone where the air masses are coming together is in the north top line, and then the southern line in our winter time. Now, if we have time, we'll talk about the El Nino and the fact that the Pacific, the range and the way that this tropical convergence zone doesn't move that much influences the El Nino. So there's very constant, strong trade winds most of the time. Okay, moving to ocean currents. So talked about the air circulation, now the ocean circulation. This is from Franklin and Folger, 1768. I think that was Timothy Folger, who was Franklin's cousin. He was a whaler. And this is before the Revolution. Franklin went back and forth to England several times. And apparently he noticed that something was going on because they would store the wine down in the hold below the waterline of the ship to keep it cool. And all of a sudden it wouldn't be cool anymore when he got to the Gulf Stream. And so he wondered about that and was probably kind of annoyed about it. Anyway, the whaler, his cousin, said that it takes a lot longer to go from Britain to America than it does the other way around. And that we're fighting a current, not just the westerlies having to tack a lot more, or all the time, probably, but also there's a current there. And so at the end of the Revolution, when the treaty was signed, he spent a week in England, and then, even though he's in his mid-80s, he basically collected data all the way back, temperature data and so forth, and at least I'm sure there were a lot of sailors and whalers and so forth that knew there was a warm current there. This, I think, is the first time it showed up in literature, scientific literature. Okay, so the Gulf Stream is part of a much larger system called the Oceanic Conveyor Belt. And so we see, we'll focus on that, and notice that it sinks up in the north. This is really important. This sinking is kind of the engine that drives the entire thing. So it's going from the orange is warm surface water, it sinks down to a few thousand meters, and then it goes along the bottom. Now there's some sinking areas around Antarctica as well, which also help drive it. And there's upwelling in the Indian and the Pacific Ocean. This part of the conveyor belt, which the Gulf Stream is part of, delivers a lot of warmth, a lot of heat to the northern Europe. If you look at England, the latitude of England, it's way the heck up there. Okay, it's the same as Labrador, only doesn't have the climate of Labrador. That is because of the Gulf Stream. Okay, so you can see on the heat map over there, even Iceland and Norway and beyond, Norway is even much warmer than it would be otherwise. And the same sort of thing on the Pacific, not as dramatic. This is just a snapshot one day, so of temperature deviations from average. So look at how, and this is from way back whenever I was teaching this, like 10 years ago. I didn't put the date down on there, but look how much warmth there is up there above what you would expect. Okay, ocean circulation. Again, the Coriolis effect is shown up there. That's those surface waters. That up on top is like a satellite data showing the warmth of the Gulf Stream. Okay, next, climate variability. Now we're going to come back to all this at the end here when we think about the tipping points. Okay, so there's long-term cycles, glacial and interglacial periods. We're in an interglacial period right now. This is on like 110, 120,000 year time scale. The main effect is that the Earth's orbit around the sun is an eclipse, but the eclipse doesn't stay the same shape. It's stretched and compressed and stretched and compressed. So sometimes in this cycle, the Earth is just closer, and the northern hemisphere gets more light. The northern hemisphere has more continental mass. Okay, so it changes things more quickly. And that's what that's from. There seems to be millennial events, which I'll talk about in a minute, like 1,500 years or so. And then like coupled ocean atmospheric things like the El Nino cycle. Oh, you can't really see the green very well, but it says just summary orbital variations. There's always been this idea that changes in the sun cycle, solar cycle have some influence. I think people think it's so slight that it doesn't really affect our climate, but it's possible, I suppose. Volcanoes can affect it because it put a lot of aerosols in the atmosphere. Okay, so here's a time record for, this is from a Greenland ice core on the left. And so the years and thousands, that's like depth going into the ice. The record is over 800,000 years. But we're just showing the current interglacial in dark blue, and then the previous one around 120,000 years ago. And notice these very dramatic swings in climate. Right? Notice that our current interglacial is pretty darn uniform. That probably allowed civilizations to develop. It might be, you think about it, it might have been much more difficult with the big swings of the past. Anyway, the idea here is that this is related to the thermohaline, the Gulf Stream and the thermohaline circulation, so that ocean conveyor belt changing. It's bringing, let me see what the next slide is. Okay, it's bringing, if you think about it, it's bringing warmth at the surface, warm water from like South Africa all the way up from across the equator and up to England and Ireland and so on. That warm water is salty, extra salty, because it's warm, it's evaporating. The water evaporates, but the salt stays behind. So as it's evaporating the whole way, and especially as it moves into that cooler, it's basically, all this energy in that current is moving to the atmosphere, and that water is getting just saltier and saltier and saltier, and it gets, salty water is heavier than less salty water. So it's getting heavier and heavier and heavier until it forms that sinking area. And that's more complicated than that. There's like 2 or 3 different areas, okay? But the idea was with these swiggles in the glacial periods, that it could be that if there were freshwater inputs into the North Atlantic, like with a lot of calving, let's say it was a little bit warmer, there was a lot of calving, breaking up of sea ice and glacier ice calving off, those are freshwater inputs right into the North Atlantic, right? And so the idea is that it's like on this is the 1,500-year cycle, it's just sort of like the ice builds up so much, there's so much sea ice, and it gets a little bit warmer or whatever, and it just starts breaking off, it melts, and then it, basically that sinking slows down or stops, and so all that warmth isn't coming up into the north anymore, and it gets very cold. It gets full ice age then. All right, so we'll come back to this. Okay, some conclusions. Uneven heating, rotation of the Earth, basically, this energy dissipating north and south. That's what drives our climate system. I didn't show vegetation maps, but it very much influences the kind of plants, where they are, and so forth. Okay, climate variability associated with variation in the Earth's orbit, oceanic and atmospheric changes, or volcanic activity. Okay, so let's move on to the greenhouse warming, and the tipping points that we're concerned about. Okay, so here's reconstruction of temperatures over the last 2,300 years, 2,300 or 2023. The last several, few decades are anomalous. Okay, there is no way to explain this warming in any natural way at all. We basically know what causes the climate to be the way it is, the way it should be, and there's no way to explain this other than increases in greenhouse gases. That's sea level rise on the top, 8 or 9 inches since 1880, and then that's partition, so it's the bottom graph is showing the same sea level rise. Part of that's just due to warming of the water, so you warm it, it expands, and then part of it's due to meltwater coming in. Okay, this, don't read all this, but I just want to make a point. 1824, a French mathematician, Fourier, realized that the Earth is quite a bit warmer than it should be based on the amount of sunlight hitting it. In fact, it should be like minus 18 degrees centigrade. Now in 1820, so we'd have an icy world, wouldn't we? In 1824, I don't know how he did that, but he did. Okay, so he somehow figured out how much sunlight was hitting France or whatever, and figured it out. And he reasoned it must be that the atmosphere retains some of the energy. That's 200 years ago. 1836, another French person, same thing. In 1856, an American woman with the contraptions and tubes and stuff that they had in 1856 showed that carbon dioxide and water vapor were greenhouse, they absorbed infrared, they were greenhouse gases. And Scottish, in 1859, John Tyndall, a Scottish engineer, he usually gets credit for it, but his experiments were more elaborate. He definitely showed that carbon dioxide and water vapor are greenhouse gases. In 1864, James Kroll figured out, basically, or suggested that variations in the Earth's orbit are what cause the glacial cycles. In 1896, Arrhenius, a Swedish chemist, basically calculated what a doubling of atmospheric CO2, how much temperature increase we would get, and it was within the ballpark of what a model would show you today. Okay. 1920s, Milankovitch basically did with pencil and paper. Okay, there's no computers, there's no AI, there's none of this stuff. It's just logic and mental work and that. Basically showed how what the orbital variations were doing to cause the glacial periods. Okay, so the point is that we've actually known this a long time. Yeah, okay, so why it hasn't just been accepted? So it's in the social realm where a lot of the real work needs to be done. Okay, that point's clear. This is the carbon dioxide at the Hawaiian Observatory, it's the oldest continuous running CO2 measurements at a place that should be free from an industrial influence. Okay, do you see any improvement? Okay, that's the point. It isn't number of EVs out there or this or that or anything else that really matter. This is what matters. Okay, so what we've done so far hasn't been enough at all. That's the point. Okay, so these non-linearities. And I'll just start off. Most of the people that study this are talking about a window of like 50 years from now to 300 years from now. Now, I've noticed that so I wasn't actually that worried about it until I started looking at new papers, and new papers are starting to say, well, wait a minute, maybe there is some chance that, like the North Atlantic Gulf Stream current could shut down sooner than that, a lot sooner. Okay, so we'll get to that. But it isn't, you know, it's like we need to worry about it because we could go, because of the previous graph, if we don't start changing that, we're going to blow by all this stuff. Okay, we're going to fall into the abyss. There's going to be nothing, and there's going to be nothing they can do about it. This is what has to change. Okay, so we'll talk about that circulation again. Again, the deep water formation is just that downwelling. That's taken a lot of heat with it down. A lot. Basically, 90% of the heat that should be in the atmosphere from CO2 emissions have gone down into the ocean. It's absorbed in the ocean in different places. And there's a concern that the ocean may not be able to hold it, you know, keep accepting all that heat. Okay, so I showed this before. The last period right before our interglacial that we're in now is called the Younger Dryas. Dryas is a tundra plant. It showed up in the pollen records in Europe when it went back to cold, cold, cold in this period. So in pollen records, they core lakes, look at the sediments and the kind of plants were there. They're recorded in the pollen. That's where the name comes from. Okay, so this was a 1,300-year cold spell that happened all of a sudden, after it had warmed up a lot. The idea here, and this is where the idea with the freshwater input came from. The original idea is from back in the 70s. And the idea was that as the glacial ice was retreating and it backed off of the St. Lawrence Seaway, the land is all compressed because of the weight of the ice. It backs off the St. Lawrence, where the St. Lawrence Seaway is now, and all this water, the Great Lakes and Lake Agassiz, has a straight shot into the North Atlantic all of a sudden. You know, like in, you know, a matter of years or whatever, huge bodies of water are emptying into the North Atlantic, fresh water are entering in the North Atlantic. And so it either caps where we need the salt water to be evaporating, it either caps it or it mixes it or both, mixes with it or both, but the water becomes, salty water is no longer evaporating, which is what causes the sinking. And so it stops. And then you go damn cold then, quickly. Okay, could that be happening now? Well, yeah, it could be happening now. This is the current. You see that blue area up there? That's called the cold blob, which is just kind of showed up in the last 20 years or so. That cold blob shouldn't be there. It's also very fresh water, relatively fresh water. So where's the fresh water coming from? Glaciers. That big Greenland ice block is part of it. Now the other thing is that as the climate is warming, there's more evaporation from the low latitudes, like at the equator, and there's more precipitation at the high latitudes. So it's also raining more there, which is also fresh water. Okay, now when I moved to Maine in the year 2000, look at the coast of Maine in North America. It's warm. When I moved here, and started learning about the area, I was told that the Labrador current would make the Gulf of Maine cooler, not warmer. And yet it's done anything but cool since then. The reason is because this conveyor belt is slowing down. That's what that means. That's what that cold blob means. Now, where the tipping point isn't clear, but it is slowing down. This is what the model says it should do, too. This is also why Europe's been getting slammed with big storms and so forth, because this cold blob is directing storm tracks further south. And so some of the big storms that they've been getting there, and the warmth as well. Okay. This is the observed warming. So that cold blob in the North Atlantic is like the only place on the planet that hasn't warmed. On the left there, that's the observed change. Again, you see the cold blob. And then the model prediction is on the right, and it doesn't have it. And so that's where, because of this discrepancy with the model prediction and what we observe, they go back and they look, okay, well, what is it about the model that needs correction? It's either not, it's an approximation. So how do we refine it and get closer? And that's where the concern came from, that we may actually be much closer to having this thermal hailing circulation shut down, which makes Northern Europe very cold, like too cold. England, Ireland, the Scandinavian countries. Now this is modeling average temperature, and again, it's not average temperature that matters, it's the extremes that matter for agriculture and for everything else. But average temperature is easier to model. It's simpler. Okay. Now, okay, that's not bad enough. See how, this is with I think this is with a doubling of CO2. Yeah, so this is a doubling of CO2. We're not there. We're 50% right now. So this is modeled if we go all the way to 100% CO2. And the thermal hailing circulation shuts down. Okay, it isn't clear that we have to do that. But it's modeling if we do. Okay, if the Amazon gets that warm, okay, those trees are pumping a lot of water into the atmosphere through transpiration. It's evapotranspiration, it's evaporation. Evaporation consumes a lot of energy, okay? So and anyway, there's a maximum temperature beyond which trees can't photosynthesize anymore. It's like 115 degrees Fahrenheit or so. They just shut down because the enzymes start to denature. Okay, so it isn't like they're just gonna keep going. They're gonna stop photosynthesizing at some point, and they're consuming. So in other words, the point is, it could be like amplifying it will amplify the warming. Now deforestation does the same thing, because you're removing trees, the area is drying where you remove it, and so again, so this is the Amazon. We're getting a lot of water coming in from the ocean, but what this drawing is showing is that, yeah, it rains like hell, but there's a lot of water that is pumped back up into the atmosphere by the trees. And so the next place where it's showing a lot of rain, it's reduced rain, but it's still a lot of rain. And so it's a lot of rain all the way from the west or the east side to the west side, even though it's not close to the ocean anymore. The trees are putting that up. So if you lose the trees, that extra water doesn't go back up there. All these species of canopy trees evolved under high rainfall amounts. It isn't clear that they're going to be able to regenerate if there isn't high rainfall amounts. Okay, so it's another thing that could be like just a cascade that keeps going. Okay, so that backs up to the other picture. If the thermal hailing shuts down and we get this warm, it could actually pressure the Amazon, even if we did stop cutting it. Okay, and this is the new paper that I looked at to get a handle on that, and it's just showing the last figure is, or the second to last figure, green and brown, it's showing a lot of areas that are protected either from indigenous cultures that are there or parks. But the center blob, it's just modeled again, well, what's happened with, if it warms that much. Let's see how we're doing for time, let's see. No, we're not too bad on time yet. So we might be able to talk about this a little bit. You've probably heard of the Doomsday Glacier. This is the Thwaites Glacier. It's a lot of ice. If it all went, it would be 65 centimeters pretty immediately of sea level rise. And it is being undercut. So this is, I forget when the top one was, but this is what's happening now. People are looking at that with underwater drones with cameras on them, and so they're able to get good data, and they're like freaking out in a way. pretty much. Okay. Then this is just a summary of tipping points. Tipping points are just what it sounds like. So if I sat on this chair and started leaning back, at some point, gravity's in charge, right? And there's nothing I can do about it. That's exactly what it is, like that. It's a feedback that it just keeps pushing it in that direction. The permafrost are, another one. There are a lot of places where it's melting and they're releasing greenhouse gases as they thaw out. Okay, nice summary then. I do like this. Prediction is very difficult, especially if it's about the future. Niels Bohr, I think Yogi Berra said more or less the same thing 50 years later, so the two of them, it has to be right. Non-linearities are especially difficult, so to predict. I was, way back when I think even before I was in grad school, I was thinking about systems, ecosystems and that, and I watched some German film of this is back in the 80s, some German engineers in a lab with a clean table. They had like a spout with sand was falling on the table, and they've got the purest, most uniform sand they could find. And they got cameras all around. Their goal is, and so it's making a sand pile. It's just dripping, like a funneling out a little bit at a time, and they're watching everything. And their goal is to be able to see if they can predict when the slope fails. So when the mini avalanche happens. Okay, so in the lab, no wind, no earthquakes, none of that stuff. Most controlled system they could come up with, uniform sand, and their conclusion was you cannot predict when the avalanche is going to happen. What they could do was they could measure the vulnerability in some way. I suppose it was maybe the angles or something. And so what the point was to me was, if these German engineers can't tell me when the sand piles, the nonlinear tipping point is going to hit, there's no way I'm going to, or anybody else can do that with an ecosystem. The climate system is a bigger version of the ecosystem. Maybe it's a little more physics involved and less of the so maybe in some ways it might be a little easier, but it's still the same thing. They can't actually know exactly when we're past it. And the concern is that we're not slowing down now, and we may just not be able to at some point. And so we just slide over it. So, okay, I think I said all that there. And okay, the final. Atmospheric CO2 is still rising. We have time to act, but at some point, it's going to be too late. The other point is the entire world needs to be on board with this, right? The whole world needs to be on board with this. Because of that, because it's a global problem requiring a global effort, I personally think, this is my opinion, the best thing we could do is really get involved in the political process and elect politicians that give a damn and acknowledge the difference and so, what's going on, and work with internationally as well. I mean, we really need to come up with some solutions. To that end, the Citizens Climate Lobby, I think there might be some handouts here. That's a local group that does just that. Gets in, tries to influence the political discussion. Oops. Also, there's a Maine Climate Action Plan, and the Brunswick Climate Action Plan is just out recently, and it's still available for comment. So that's in the kind of the realm of getting your own house in order. But we do need to think more broadly as well.
Topsham is also working on it.
Topsham's work, okay, Topsham too, yeah. That's all I have. I hope it wasn't too depressing. I do think it's, I think it's important to know to really know how things work and what the issues are, so we don't think we're doing a lot when we're really not.
Yes.
Okay?
Yeah.
Yeah.
And is that at all related to some of your thoughts on the Amazon?
Yeah, so the deforestation is like 18% of the original area. The models are showing like, and so that's sort of becomes savanna then. It's not like it's all just returning to rainforest or pasture or whatever, right? Okay, so that is, it's not the same as the rainforest at all. It's much warmer at the surface. Again, those trees are converting a lot of energy. They're consuming a lot of energy through evaporation. They're pumping water from below the ground and out the leaves. That consumes a lot of energy. So if you think about it, where's the warmest places on the planet during the summer? I mean, where's the record heat? It's at like subtropical. It's not at the equator. Why is it at the equator? I showed you the temperature thing already. Because there's a lot of trees down there.
Yeah, apparently there's a drought in the Andes as well. That's one of the things they've warned us about.
Right. So we just went through a major El Nino event, and that shift a lot of it shifts the rainfall patterns where they do get droughts in South America in places that are normally wet. It's usually for a year or two, and then it starts swinging back the other way. Yeah, Doug.
I just learned a ton, so I'm going to be a while catching up here. But one of the things that struck me that you didn't comment very much on, except for the Franklin slide, were the dates of some of our basic understanding.
Yeah.
And what I took in was that our basic understanding of climate is 18th century science. And our basic understanding of this pattern of change is 19th century science. Is that right? And have we just been refining and measuring better and gasping for the last 100 years? Is that what's going on?
I would say we're filling it. So in the 70s, I didn't read all of them, but the last one was in the 70s where they had mainframe computers. A husband-wife team and their students really ran through the orbital variations and showed with a computer running for a month or something, right? And what they showed was, yeah, the Polish astronomer from the 20s was right, but they couldn't get the ice ages to form. So they sort of basically looked backwards where we kind of know what happened to calibrate and then aim it forward, okay? They couldn't get the ice ages to form until they added CO2 changes. Okay, so during the ice ages, CO2 is amplified. When the orbital variations say get colder, the oceans are cooling, the cooling oceans can hold more CO2. And so CO2 is going back and forth between the water and the atmosphere constantly. But just because it's cooler, it's holding more. Okay, and then coming the other way, as it warms, it's coming out of the ocean. And so that with that feedback, it amplifies the change that the orbital variations makes it go even further. Then they got the ice to form. And so I think you're more or less right that a lot of the big ideas, it isn't just in climate science, and it's in a lot of things that, the big, maybe it's in a way low-hanging fruit, I don't know. The big things are they can only be discovered once, right? I mean, Darwin, people have been, modifying on Darwin. It's important to show that it's true, too. That a lot of things that are logical, nature has a lot of different ways to get to the same endpoint, and you have to show that that's actually how it works. Because it could have maybe gone this way or the other way, and we need to know which way is real. But yeah, I don't disagree with what you said. Yeah.
Can you please comment on the degree to which the probability or likelihood of crossing tipping points, let's say the AMOC tipping point, increases as a function of the increase in the global surface temperature? Notably, is it going up probably linearly? So 1.5, 1.6, 1.7, 2, and on up.
So that last figure with all of these different potential tipping points had it had degrees of warming. So I think the lowest was less than 2 degrees centigrade warming. Okay, you know where we are this year?
1.2 or 1.1.
We hit 1.5 this year.
Oh, well, temporarily, but.
Temporarily, right. Yeah, so it's like, I think we're at 1.3. It's the El Nino kind of warms things up quicker and it should drop down a little bit, but we're pushing our luck, right?
I just think that's so important for people to recognize. And you did make the point that, we still have some agency about this. We can still do stuff. And rather than, thinking about dropping over a cliff, I think you used words, dropping into the abyss were your examples. I mean, I would prefer to think about, yes, every 1/10 of a degree centigrade matters. Everyone is pushing closer to the tipping points. I don't disagree for an instant. I read the AMOC piece, the Ransdorf piece that scared the heck out of me.
Yeah.
But I want to tell people that we still have agency.
Yeah.
Yeah.
Join CCL.
Yeah.
Right. Good point. Now,
You haven't mentioned biodiversity. You could put in, here's another, if you really want to get depressed.
we're good at that, aren't we? Yeah, we could have. I mean, the coral reefs are into the tipping point right now. Now, a lot of these, we tend to think on yearly timescales and that. So a lot of these are kind of more geologic timescales. So they're talking about, a couple hundred years for all the ice to disappear, which on a geologic timescale is like a half a second, right? It is a tipping point, but it's a big block of ice takes a while to melt too. So it's, again, yeah, there's time, but there's a lot of reason to be concerned and to, I always think about it, we need to really think about what it is, where's the most important place to put the effort that we have, that we can manage. And again, I think it's, just look what happened with this election. I mean, we'll be backed up at least 4 years, right? And who knows how much damage. So it's like, that's probably job number one.
I think it's local too. It's local elections. It's our people here in Brunswick,
Ellie?
I was just going to say it's important to point to the information that the Citizens Climate Lobby has over on the farm wall. And there's some representatives here that can.
From the Citizens Climate Lobby? Okay. Did everybody hear that? A Citizens Climate Lobby is a local group that is interested in influencing the political discussion. And there's information on that way. Yeah.
I heard what you said about politics, but a little bit more on the more technical side. How would you prioritize your top 2 or 3 things that could change this? Of all the menu of things that are happening, if we were able to reach through and influence things, what would be the most?
What would be most likely to do something about?
Yeah.
There's probably a lot of methane leaks, from natural gas wells and piping and stuff. That wouldn't be a bad idea. It seems to me that they just flare off because it's like a waste product. And in the shale oils, it's like a waste product practically. And look at a map at night, like a satellite view of South or North Dakota, one of the two, like the western side. It's all lit up. Those are gas flares.
Right.
And now, not all that gas is burned. I mean, they want it to be, but it isn't necessarily. That's probably the one thing. The CO2 in the atmosphere is really going to be there a long time. Methane doesn't, it's very potent as a greenhouse gas, but it doesn't last as long. It just interacts with things in the atmosphere. The carbon dioxide has like a half-life of over 125 or 150 years. And so it's up there for 1,000 or more years with elevated levels, probably a couple thousand years. So, you know, it's like, you know, how do you stop burning coal? That'd be the best thing right now. There's a lot of work on small fission reactors. There's corporations that are doing that. I mean, there's been breakthroughs on, at least in the lab, on fusion. You know, the Brits and other Europeans have had sustained reactions at the lab, at least that last a while. That would be the ultimate, I think. But people have been saying that for a long time, too. There's nuclear submarines running all over the place that have small reactors running them. And there's other kinds of fission reactions that don't require high pressure steam, which is where the real danger is. Now, yeah, there's waste products, but there's trade-offs every which way you look. We have to deal with the waste products. I mean, that's, I can't think of a better thing right now. Maybe there is something, but, and it's, you know, it's not like I know that much about it and more than anyone else about that. Yeah.
I'm just sitting here, I'm not affiliated.
Oh, you're not?
No, I'm just sitting here. But part of the things I wonder about is the tracking the movement of peoples as a result of the change. And I'm worried that people might use that data not to provide relief, but maybe to limit.
Movement?
Yes. And that's one of those areas where I do wonder, because that's something that could be used both, like, you know, they say the axe that builds can also destroy.
Yeah. You might be right.
Thank you, John.
Sure.